All right, thanks everyone for coming. Looks like we've got several folks on Zoom as well. We're here, ladies and gentlemen, for the master's thesis defense by none other than Alex Spengler. It's going to be exciting. I just want to give a quick introduction to Alex. I met Alex right when I started the current position I have here at UH. And we've seen Alex change over the years, gone through a few hairstyles. But early on, I noticed Alex is an exceptionally intelligent student. He did really well in classes. It was really obvious he was smart. He stood out, but more than just the intelligence, I think what was really intriguing about Alex's ability was his creativity. So he looked at a lot of things in classes and science differently, and that's a special skill set, especially today. You know, it's hard to be able to have a creative mind. You can train people in a lot of analytical techniques, you can teach them information, but to have that creativity to look at things differently and want to kind of expand how science functions is a special skill set. And we really appreciated Alex's view and what he was capable of. And so he started working with me right away, actually in the Mega Lab. And I can honestly say Alex played a really formative role. It's kind of a strange thing now to get to the end of his time, because he's been there since the inception, when we were just a small study room in the library with a little name written on a chalkboard. And you know what Alex has brought to our group is really immeasurable. And it's, again, not just the science, it's the way he creatively thinks about outreach, which you'll hear about in his master's defense today. But he's played a really monumental role, and I just want to give him credit for that. You know, you won't be able to escape us, unfortunately. We'll try keep working around with you, but we really appreciate you, Alex. So we're excited here for your defense. And with that, I will let you take it away.
All right. Thank you. All right. My name is Alexander Spengler, and today I'm going to be presenting my master's thesis work, kind of what I've been working on over the last 3 years. And my title is Sea to Digital Reality, an analysis of underwater photogrammetry platforms and augmented reality. And so my thesis is broken up into 2 distinct chapters. And the first chapter is a comparative analysis of photogrammetry performance underwater between an established and emerging camera platforms. And I use this word like underwater photogrammetry. Why do we care about underwater photogrammetry or doing photogrammetry underwater? Well, I'm viewing this problem through the lens of a coral ecologist. And ubiquitous to coral research in the modern era is underwater photogrammetry. It allows someone to enter the underwater environment and capture a whole bunch of data in a short amount of time. And usually time is limited underwater on scuba, or even if you're snorkeling, your time's kind of precious in those environments. And coral reef systems are unique and precious in themselves. They cover 1% of the earth, or 1% of the ocean, and are home to 25% of the marine biodiversity. And they're foundational to these marine ecosystems, not only in a literal sense in their calcium carbonate skeletons, but also in their support for life and biodiversity. They also slow down wave energy and support surf communities. They provide a bunch of beauty. The biodiversity that they bring, the species, supports beauty, and coral reefs serve as a natural wave break too. They naturally slow down wave energy that can protect nearshore areas. It can protect them from erosion or wave inundation. And they're also hotspots for discovery in the fields of biomedical research, climate change research, and of course, coral reef ecology. There's a lot of unknowns in coral science. And a lot of coral science depends on a whole bunch of people to make happen. Coral reef environments are often geographically isolated or distant, and at the largest level necessitate research cruises to travel thousands of miles to far off atolls to collect science. And there's this dance of logistics, bringing trained specialists to a certain dive site or to a certain reef safely. And once you get to that place, it's important to make the most of your restricted time. And I'm visually making a parallel between science divers and astronauts here, because I don't think us as scientific divers give us enough credit, ourselves enough credit. I like to kind of think as a scientific diver as maybe like an astronaut that chose the sea over the sky. It's all to say that when we're in these environments, collecting as much data as possible and high quality data is paramount. In the general overview of this first chapter, kind of my main objectives is to do this comparative analysis of underwater photogrammetry performance between established and emerging platforms. And what do I mean by that? Well, not everyone that is interested in doing photogrammetry underwater has the same data quality requirements. Not everyone's after the same thing. Some people might want to collect data that is high enough quality to publish in a scientific journal. Others might just want to generate some data products that they can share with their community or legislators. And not everyone has the same environments. We're fortunate here to have access to reefs where we can snorkel and we can get an intimate experience with corals without diving. But other people, those reefs might be inaccessible due to wave action or just the depth of the reef. It can be hard to get close to them. And not everyone has the same means. Not everyone has the same budget or access to the same scientific equipment or cameras. And so with this, I hope to kind of compare some camera platforms and help optimize research methods so that users can make the most of their tools. And photogrammetry, I'm kind of getting ahead of myself a little bit, but photogrammetry, and specifically structure from motion photogrammetry in a underwater setting happens when a scuba diver kind of swims in a zigzag pattern over the reef. And they're swimming and collecting imagery that overlaps in that zigzag or like lawnmower-like pattern. Those images from the camera are then brought into photogrammetry software, where identifying points like the same little area of a coral is detected in multiple images. The software can use those points of confidence to assign a point or a tie point to a specific area. And kind of similar to how our eyes get depth information, the software can take 2D images and create a 3D model. And we're all kind of doing that right now. We have these two, biological cameras that are feeding our brain images, and our brain's doing some impressive calculations to measure the distance between those incoming images, and we have some perception of depth because of that. And the fundamental 3D model building behind this is similar, where you're kind of comparing imagery. From those 3D models, researchers are able to export orthomosaics, like a large panoramic image of the area, as well as a digital elevation model, which retains that depth information. Researchers can then annotate or trace out species, disease, growth, size, etc. on those orthomosaics. And that can in turn inform the who, what, where of coral reef ecology. With that digital elevation model, researchers can calculate the structural metrics that kind of describe a habitat, things like complexity, vector ruggedness, slope, and curvature. And with that, kind of characterize the habitat. And a super important and powerful part of this analysis is those two end products are tied together. The habitat metrics are tied to those ecosystem metrics, or those biological metrics, allowing researchers to come to some very powerful conclusions. And this is all due in part to the camera. And fundamental to cameras are imaging sensors. And a sensor, a digital sensor, takes in light or photons and converts it into an electronic signal. And the signal the sensor that most cameras use today is a CMOS sensor, or complementary metal oxide sensor. And technology has progressed over the last few decades, allowing those image sensors to get smaller and more dense while still producing high quality and higher quality images. For this study, I've divided the cameras into two general groups. And one is DSLRs, or digital single lens reflex cameras. And the other category is action cameras. And DSLRs have kind of ubiquitous use currently in underwater photogrammetry for coral ecology. A lot of professionals use them. However, the size of the camera and the lack of weather sealing necessitates an underwater housing specific to the camera model and the camera lens. Action cameras emerged in the 2010s with the advent of the GoPro Hero series and quickly exploded in popularity. Oftentimes they're weather sealed or come with a waterproof housing and offer simple ease of use and generate high quality imagery. The representatives that I've chosen from these two groups for this study are the Canon 60D and the GoPro Hero 4. Now, the Hero 4 has a 92% smaller image sensor than the DSLR here, the representative DSLR. And to illustrate that size difference, the sensor on the right-hand side is 92% smaller than that on the left. It generates 66% smaller images. It's got a teeny tiny lens, 87% shorter focal length, and at release was 71% cheaper than the Canon 60D. Now, when you account for an underwater housing, it brings that difference up to around 90%. And it's important to note that both these camera platforms are pretty dated now. Both came out in the 2010s, but they're both proven and reliable platforms. The Canon 60D has been proven in marine science to generate high quality imagery in an underwater environment. Here I have a representative example. Hopefully you can see that on Zoom and the resolution isn't too crushed, but you can make out fine detail in that coral head. The GoPro Hero 4 is also dated, but this is an image from the late 2022 NASA Artemis mission, the mission back to the moon, the manned missions back to the moon, and it was taken by a GoPro Hero 4. So that the 2025 and 2024 manned missions to the moon utilize GoPro Hero 4s. Now they have a modified case, of course, for space, but that image sensor is the same. Now, to compare these two platforms, I collected data at the same time, simultaneously, on both camera platforms for the same area. That allowed me to generate a twin set of images. So images from the GoPro went on to make a 3D model, an orthomosaic, and DEM, and an image set from the DSLR kind of did the same thing. And to evaluate quality between the 3D models, I used metrics that were relatively standard for measuring quality in 3D models and photogrammetry derived products. The first of which is ground sampling distance, or GSD. Now, GSD can be roughly associated with resolution. On the left-hand side of the screen there's an orthomosaic with a 10 centimeter per pixel GSD, and it should visually appear more coarse, or it might be harder to make out fine detail than the one on the right, which has a 10 millimeter per pixel resolution, or GSD. And GSD is based on 4 parameters, based on distance from your subject, focal length, sensor size, and image size. So theoretically, you could compensate for a small image sensor or short focal length by shortening the distance between subject. However, if you're really close to your subject, you're going to be capturing a smaller footprint, smaller image footprint. Action cameras like the GoPro Hero 4 have a wide-angle lens, or a fisheye lens, allowing to catch a larger footprint at that short distance. I've also chosen to compare spatial error. And spatial error is the disconnect between a known measurement like the scale bar here, and that measurement's in the 3D reconstruction. I've also compared reprojection error, which after the model has been made, the reprojection error is the error kind of reflecting back on the original photos during the building process and checking the difference between the error made there between the 3D model. I've also chosen 3D model parameters like tie point density, point cloud density, and mesh face density. And I mentioned this earlier, but tie point density are those points of agreement. So when the software is looking at the images and can identify a common spot in multiple images, it assigns a tie point. It does that 100,000 times, 1,000,000 times, and you can use the software uses reference imagery or imagery, contextual data from the rest of the imagery to kind of fill in the blanks, to kind of add, to flesh out this proto 3D model. And with that contextual data, you're able to build a point cloud. And the point cloud is kind of like the fundamental part of the 3D model. It's kind of like the lowest unit almost, the most base unit. And on top of that point cloud, if you connect all those points in the point cloud, you're left with a mesh face. You have a bunch of faces like little triangles in between the areas that you've connected. And finally, to evaluate model quality, I superimposed or measured the distance between those kind of twin point clouds to one another. If they were exactly the same, there'd be no distance in between those 2 point clouds. And to represent this, you're left with an image or a figure, or I generated figures that look like this. So the main takeaway with these figures that you'll see later on is if you see color, that indicates distance between those point clouds. That's areas where they separate or differ. So here we can see greens, red or yellows, blues around the edge of the point cloud, indicating that there's some separation between the kind of paired point clouds there. And those were the 7 model quality metrics I evaluated. I also looked at habitat structure metrics that are commonly used in coral reef ecology. So I looked at vector ruggedness, which is like the angle of those faces. So if an area is really rugged, the angles are going to be sharp or not flat or kind of positioned planar. I also evaluated slope, which is change in elevation across the adjacent cells in the DEM. Curvature, which is how concave or convex cells are throughout the DEM. And finally, surface complexity, which is the ratio of the 3D area over the 2D planar area. And all of these metrics are dependent on the digital elevation model, or that DEM. And it's important for me to say that for this study, I exported the DEMs at 1 centimeter per pixel. And that's a standard. That's like a publishable standard for underwater habitat structure metrics in coral reef ecology. But it defines the threshold for measurement. So if you are interested in these habitat metrics on a millimeter scale, you wouldn't be able to detect that. It wouldn't be an appropriate analysis to make. And finally, I looked at how distance from subjects changes between these platforms, or changes those metrics. To do this, I performed a structure for motion photogrammetry survey at 1 meter and used my dive computer to get 3 meters away, and then 6 meters away, and 9 meters away, performing 4 sets of paired imagery for a given area. To improve the power of my analysis and to account for any errors in measuring distance with the dive computer, I kind of group these into 2 categories. So from 1 to 3 meters from the subject, I termed as close, and 6 to 9 meters far. And I had 2 study sites First was Lehala here on the Big Island of Hawaii. And it's located on the east side of the Big Island of Hawaii here in Hilo. And it's a super cool spot. It's accessible, it's protected, and there are hundreds of corals that are easy to survey and appreciate just using a snorkel. For the distance from subject analysis, I went to Mahukona, and that's located on the northwest side of the Big Island of Hawaii. And it's another accessible area, accessible for snorkeling and scuba diving, and is frequented by members of the community. But this just afforded depth for those scuba surveys. To do all this, I collected imagery on the rig on the left there, and I collected over 20,000 images and built 54 3D models, orthomosaics, DEMs, point clouds, and that resulted in 27 paired models, orthomosaics, DEMs, and point clouds I was able to confidently match together. And I measured the distance of over 310 million cloud points. Kind of looking at the results qualitatively. Here on the top is imagery generated by the Canon 60D. So you can see rich colors, a more balanced exposure compared to the imagery at the bottom from the GoPro Hero 4. And that's kind of to be expected. The sensor is a little bit better. The white balancing capability of the 60D is better than the GoPro. And the GoPro appears less vibrant, or the imagery produced by the GoPro, and kind of overexposed. It looks white to the eye. And there are some other errors or artifacts coming up in the GoPro imagery. It's just chromatic aberration, which is kind of that ghosting effect that you might see on the edge of certain objects. And that's when light enters the camera lens and separates, and then fails to reconverge at the same spot on the sensor. And so it kind of smears. And this can introduce errors in a lot of those 3D model parameters. There's also noticeable bending at the edges of the imagery. So these images were captured at the same time, and that scale bar should be the same size. But the GoPro scale bar looks a little bit longer and almost kind of curved. And that's due to the fisheye lens, or that wide angle lens on the GoPro. A lot of these trends carry through to the 3D models generated from these sets of imagery. The DSLR, those rich images made for more rich, balanced exposure in the 3D models. However, kind of new is it's a smaller area. It captures a smaller area during the same capture time in the same area. Whereas the GoPro, afforded by that wide angle lens, or that fisheye lens, is able to capture a larger area, or to build models of a larger area. And moving into the model quality results between the platforms, reprojection error and GSD were significantly different between the two camera platforms. And reprojection error, as I kind of mentioned earlier, is one of those parameters that really suffers from things like chromatic aberration, or the stretching or bending of certain objects in that 3D model. GSD is, again, kind of hardwired or tied into things like the size of the camera sensor. So we'd also expect that to be worse for the GoPro. But it's important to note too that these are both generating pretty high quality imagery, or GSD values. So they both have medians here around or under 1 millimeter per pixel. Cloud density and mesh face density were also significantly different between the two platforms. And these parameters are very closely related. They're, as I mentioned before, the mesh face is built upon that point cloud. So you'd expect these to kind of behave similarly. And higher quality imagery allows you to build more points in a point cloud and more faces in a 3D model. So there's nothing surprising here. This is what we'd expect. Now, spatial error and mesh face density, neither of these were significantly different between the platforms. However, there are some slight differences in the median values here, where the GoPro is still performing a little worse, but not significantly, producing more error and less dense mesh models. Now moving into the point cloud comparison, again, where I kind of aligned and measured the distance between 2 point clouds. Overall, for near subject plots, on average, the plots were 0.88 centimeters distant from one another. And so in an ideal, if they were perfect, it'd be no distance. And the median was 0.61. And I underline across near subject plots here, because as we'll see later on, at far distances, 9 to 6 meters away from your subject, the GoPro imagery was pretty coarse. It was hard to discern fine detail and struggled properly reconstructing things like scale bars. So it wasn't appropriate to align that to the imagery produced by the DSLR. And to kind of illustrate this further, here's a low difference in distance example from 2 point clouds. So again, the big takeaway from these is if you see color, you're seeing distance. And more color means more distance. So in this low difference example, the colors are relatively washed out, and there are a lot of whites indicating no distance between those kind of twin point clouds. But there are some trends that carried throughout the entire data set. So there's mild distances at the center and along the edges where there's like yellows and greens at the center, indicating some difference there. Now, as we move on to a larger plot, a plot of a larger area in a more structurally complex area, we see some high differences, some reds now, some bright greens, indicating much more difference between those 2 point clouds. And this indicates that there are some separations here. So this area is more, it's larger, and it's also a little bit more structurally complex, and it likely indicates that the GoPro is struggling to properly reconstruct this 3D environment. So the green in the center might be because the GoPro tends to skew imagery when it's close to a subject. And at the edge of the 3D model here, the point cloud, there's that red coloration, and that's parts of the model that is just reconstructed on fewer images. And GoPro images tend to flare out or skew at the edges of the individual images, and that might indicate some flaring kind of between the two models, where the DSLR might be flat and the GoPro might be artificially flaring the model or introducing error. Moving into habitat structure metrics between the platforms, curvature was significantly different between the two platforms. And again, it's important to reiterate that the DSLR can capture higher quality images, and the GoPro is producing lower quality images. And I suspect that these lower quality images might be artificially kind of smoothing over a lot of the detail and some of these DEMs. It might be kind of simplifying this. And what I mean by this is, it's kind of painting with a bigger brush. It's making broad strokes with the lower resolution of the imagery from the GoPro. And I think this is the reason for the difference in curvature here. Neither VRM, surface complexity, nor slope were significantly different between the camera platforms. And it's important to reiterate that these DMs were exported at 1 centimeter per pixel. And the differences between these three parameters might be lost in that analysis. So theoretically, if you were able to export the DMs at a 1 millimeter per pixel resolution, you might be able to detect some differences between these platforms. However, at a 1 centimeter per pixel scale, there was no significant difference. And moving into that depth analysis, or the distance from subject analysis rather, qualitatively, 1 meter from the subject, the images were pretty high quality. We're able to resolve a high level of detail. So in the bottom right of these images is that GSD, that kind of resolution value, and they're both pretty low. And you can see the spines on an urchin, you can see the tick marks on a scale bar. However, there are some differences. The GoPro suffers again from white balancing issues or overexposure issues as evident on the slate there. And in the DSLR imagery, you can detect different grain sizes. You can see different coloration in the sand, and that's kind of lost in the GoPro imagery. Moving to 9 meters from the subject, the GoPro imagery kind of breaks down at this point. Most of the detail is lost. So you can't make out, even if that was an urchin, and the ticks on the scale bar are lost. And the DSLR imagery, you can still make out those same things. You can still see, maybe not on the projector here, but you can still see the tick marks on the scale bar and the spines on an urchin. And it's also important to note that the difference between these two GSDs is the same. It's still about, the GoPro is still about 2.5 times greater GSD. If you were paying attention, the other one, it was about 2.5% greater as well. And now looking at these model quality parameters between the platforms over distance, spatial error was significantly different only at close distances from the subject. And the far distance was not significant, but it's important to note that there's a pretty significant range in that GoPro data, indicating that there's something kind of funny going on there. And I suspect that this is kind of the functional breakpoint for the GoPro. Reprojection error and GSD were both significant at both distances between platforms. And again, reprojection error and GSD, we expect these to be, as they are increasing in both error and GSD as you get further away from a subject, as your image quality gets worse. And we'd also expect a camera with a smaller sensor to perform worse in these situations as well. For the density metrics, the majority of these density metrics, tie point density, point cloud density, model face density, were not significant, with the exception of the point cloud density and model face density at far distances. Those are the little tiny like sliver box plots there. And again, all these parameters are interlinked and should look similar, and they do across the 3 figures here. And the most striking thing with these 3 graphs is the performance, or the performance range of the DSLR at 1 meter from the subject. It's creating some really high density 3D models at that 1 meter from subject distance, indicating an area where this platform might be really potentially excelling. And to kind of describe this visually, all these parameters over depth, here's a PCA plot where these 3D model quality metrics are represented along with the 2 camera platforms. So, ovals that are orange or brownish are going to be for the GoPro, and bluish for the DSLR. And those that are close distances are going to be more vibrant or brighter, and the far distances are going to be the lighter of the 2 colors. Now, there are some interesting trends here. So just like I mentioned, on the right-hand side of that plot, you can see all those density parameters kind of pulling away and inside of that DSLR close bubble, indicating a strong relationship between those. Also of note is you can kind of illustrate the action camera braking as it's far away from the subject, where it's going at a right angle from the rest of the ovals here. And there's also a lot of overlap between these platforms that's important to consider. So here we have, when the DSLR is far away, it's almost completely inside of the action camera close, kind of implying that these are behaving similarly. They have a similar relationship. Now, 3D habitat structure across distances also had some interesting patterns where curvature at far distances and surface complexity at far distances was significantly different between the platforms. Now, I mentioned before that fisheye flare at the edge of the plot. I'll talk about that in just a sec, but the curvature might be impacted by the low quality of the action camera. Again, kind of artificially smoothing that model. You might lose some curvature there, and that's where I suspect the difference comes from. Now, with the surface complexity, the GoPro is producing results at a far distance where surface complexity appears to be artificially inflated. And I think that this is likely due to the flaring at the edge of the GoPro models, where it's kind of separating or introducing a lot of air, kind of like in the red areas in that distance comparison plot. Neither slope nor VRM differed significantly between the platforms, and both decreased with distance, but again didn't differ significantly between these two camera platforms. And just like I did with the quality metrics, I graphically represented these on a PCA plot. And here you can see like the standout, the curvature metric kind of being strongly associated with the DSLR close. Again, kind of indicating that this camera performs really well in a close environment. And just like the 3D quality metrics, there's a lot of overlap with many of these metrics. So DSLR far is fully encompassed in action camera close, and has a lot of overlap with action camera from far away too, indicating that these are kind of performing similarly and have a similar relationship to these parameters. Now, what does this all mean? So for model quality metrics between platforms, there were significant differences in reprojection error, GSD, point cloud density, and mesh face density. So if you're interested in these parameters, it's probably more valuable for you, or you're going to get higher quality results if you choose a DSLR over an action camera, or a camera with a larger sensor than one with a smaller sensor. And that trend, or the same pattern, exists for curvature, for habitat structure metrics. So that was significantly different between the two platforms. And so again, if that's a metric that is important to your study or what you want to communicate, a higher end camera platform might be more beneficial for you in this case. However, it's important to note that for this study, these metrics were compared using a 1 centimeter per pixel DEM. So your mileage may vary if you break that down into a smaller or more fine resolution. And with distance, these relationships kind of became more complicated between the platforms. So at close distances, reprojection error, GSD, and spatial error were significantly different from one another between those platforms. And so if your environment allows you to get close and you care about these parameters, or they're valuable to your research or your question or what you want to communicate, then again, you might want to choose a higher end camera. Now, as we'd expect, as we get further away from the subject, more of these parameters become kind of connected or dependent or affected by differences in camera platforms. So reprojection error, GSD, point cloud density, mesh face density, surface complexity, and curvature were all pretty different between the two platforms. And again, if you can't get close to your reef, if you have to survey it from far away, it's probably better to use a camera with a larger focal length or a larger imaging sensor, like a DSLR. And so what does this all mean? So I was motivated to kind of explore the potential in applying scientific methodology to a cheap action camera in hopes of democratizing science, kind of opening up the door, asking, what if? Do we always have to survey reefs with a DSLR? Or can we use other cameras that are more readily available? And I found that the GoPro Hero 4 will not provide the same quality for all metrics, but it's important to kind of consider, what you're asking, what your end products What do you want in an end product? What does your environment look like? What does your survey environment look like? And what are your means? What's your budget? How fancy of a camera can you get? As well as, or as with this, kind of moving forward to looking forward, we are breaking down barriers to science, and that's a good thing. From 2009 to 2019, GoPro sold 30 million GoPros. And the GoPro Hero 4 used in this study is basically a free camera in 2023. It's like 20 bucks or something. And that's a lot of data science collection potential, or just the potential to survey your reef in a pretty powerful way. Not everyone necessarily needs to generate models that are publishable. Maybe again, they just want to communicate those to their community, or to legislators or change makers. And that leads into the second chapter of my thesis defense, titled An Immersive Exploration of Pacific Coral Reefs and Wrecks, an Augmented Reality Application Leveraging Structure from Motion Photogrammetry. Now I'm going to grab a drink of water, and if you want to download my app, I have 2 QR codes here. If you're in the room, the QR codes might not show up very well on the projector. You might have to pinch and zoom in if you want to download. But if you want to download my app, you can use the QR codes there. It's titled MegaLab AR in both Android and iOS app stores. And for those of you sitting in this room, there are AR targets underneath all your seats. All right. All right, so moving into the second chapter of my master's thesis, I was interested in communicating science in novel ways. And here in Hawaii, we have access to reefs unlike most reefs in the world. We have, you can almost see the ocean for where I am here, and that's a pretty unique characteristic to have. The majority of people have a relationship to the ocean through media consumption. People are inspired by documentaries, or they learn about coral reefs through Netflix documentaries or BBC documentaries. And just on the topic of novel ways to kind of build a relationship with the underwater environments, here on the Big Island, we have a live stream cam over on Kona that lets you take a live look into coral reefs, streaming 24 hours a day. And it's the through line with this in my thesis is that it opens the door to science. There's a bunch of science projects that are running off of this camera. It's not only entertaining to look at, it kind of has like a campfire effect for me, where it's always entertaining to look at. But there's also a lot of scientific potential with this. Research projects on training AI to identify fish, or to compare how do surveys happen underwater versus underwater through a camera versus through scuba or snorkeling. And these questions or sharing science is pretty important to me. And so I created the MegaLab AR app. And the MegaLab AR app is an augmented reality application. And what that means is that it lets you see a digital object kind of in the real world. So it's like VR without the headset. So here I am interacting with targets, those kind of QR code looking things on the bench there. And when I bring the device over it, the application superimposes a 3D model, and a 3D model generated through structure from motion photogrammetry. The user experience looks something like this, where again, you bring the camera or your phone camera over the target, and you'll see a 3D model from a coral reef or a shipwreck or something. And there's ways to interact with it. There's site information, educational content. And inside the app, there's access to to areas throughout the Pacific. So from all the way in Guam, you can visit or interact with wrecks from World War II, to Papahanaumokuakea, the Marine National Monument here in the northwestern Hawaiian Islands. You can interact with the most pristine reefs in the world, Oahu, and the Big Islands. And in building this app and kind of tying back to that first chapter of my master's thesis, I'm using those photogrammetry assets, those 3D models, and moving them into the app. And oftentimes they're pretty large. They can be several gigabytes individually. And if you're storing that on your phone, that can make for a pretty big app. So I cropped them down and decimated them, which is a cool word for just reducing the number of triangles in that mesh cloud, if you remember that in the model building process that I described earlier. And lastly, I reduced the texture resolution to still retain some of the detail, but to decrease the file size. And I leveraged the Vuforia augmented reality engine to do all the target tracking. So those targets are those QR code-like objects, and Vuforia allows me to associate those with a 3D model. So this is what the development view looks like a little bit, where the 3D model is actually superimposed on top of that. And that's indicating kind of the user experience, so the orientation of that 3D model. And in practice, it looks something like this, where again, that 3D model is superimposed on that target. And essential to all apps is building a user interface. And so this happens in the Unity gaming engine, which is an app engine or a free software engine that allows you to develop apps or programs. And I developed the user interface to be clear and easy to use, and also scale between phone sizes. So the app is available on both iOS, so Apple devices, or Android, and those devices have a large range of screen sizes. And this is something that I certainly haven't perfected, but the app works on tablets and phones pretty well. And some of these concepts are kind of abstract, just AR and having a target might not be intuitive. So the app begins with a tutorial sequence that's skippable that kind of instructs the user on how to interact with the app. In late 2022, I integrated AR video targets. So I realized that I didn't have to have augmented reality targets that look like those QR codes. I could use imagery or logos that might be on stickers or shirts, and associate those with a video player or a plane with some light scripting. So that experience looks something like this. So when you bring the camera over Megalab logos or certain imagery, you're going to see a short video clip or an animation play that's relatively seamless and can make a otherwise static area feel a little more alive. And so the app has 20,000 impressions on iOS, and that's just basically people looking at the app listing, 1,500 iOS downloads, almost 150 Android downloads, and is a proven outreach tool. So here's examples of the app being used in a bunch of different capacities at a museum setting where people are interacting with the app. Out in the field, the app doesn't necessitate an internet connection. So if you don't have internet access, you can still interact with the app as long as you have it downloaded ahead of time, of course. And a classroom setting. And this is all to say that the app is pretty intuitive to use. You can hand it off to a kid or an adult and show them one example and let them explore. I like to imagine it kind of as like a digital magnifying glass where they can interact with the world around them. And it's unique, and it's one of the few ways that you can tangibly interact with your taxpayer dollars that go to research. You can hold that whole science supply chain, the end product, in your hand. You can have a 3D model of a reef that exists thousands and thousands of miles away from you. And many times access to these areas like Papahanaumokuakea are limited to research or other specific things. And I'm kind of getting ahead of myself there, because a lot of these sites you need to dive in, and not everyone is scuba certified or able to dive. And it's the easiest way to teleport. So again, it can bring you to Guam, it can bring you to the northwestern Hawaiian Islands. You can travel around space, and you can also travel through time. So a really cool part about a lot of this science is you're capturing the environment as it was when those scuba divers or those snorkelers took all those photos. So there are a lot of things that change, and that's certainly true with coral reefs. So in the bottom right is a reef called Rapture Reef in the Papahanaumokuakea Marine National Monument, that Lalo, and it was obliterated by a hurricane that came through. So today, if you went there and in scuba dove, if you teleported there right now, you'd see a field of rubble. You wouldn't necessarily see any corals, or maybe little baby corals. But if you went back in time to say like 2017, you'd see a flourishing reef. And right now in the Megalab AR app, there is a flourishing reef from back in time. Here in the Big Island, we also have reefs like Waiʻi that don't exist in the same capacity anymore. They're underneath lava. So theoretically, you could look at those and experience reefs that don't exist anymore. And for future work with the app, I have a lot of kind of big ideas where the Android app is a little outdated compared to the iOS app, but I'm also really interested in using SLAM AR or AR that's targetless. So here's me kind of prototyping out a targetless AR experience. And the way this works is it uses the phone's, like GPS, internet connection, and inputs from the cameras to kind of position your phone in space and project or augment a 3D structure in that area. And it can be really cool. You can walk into it. These are scientifically generated models, so they're accurately scaled, so you can see how big a coral is or how big a shipwreck is. And that's pretty cool. And I would also like to have maybe like model packs that you could download, where you could use this as an educational tool. So you could have really high resolution 3D models of corals and to train species IDs to researchers or members of the community. You could also do that with disease, where you have disease corals. And I'd also like to develop maybe a sister app where users can collect images and build either on a GoPro or on the phone themselves, and build that model on a GoPro. And Crispin and I are kind of working with the Megalab and WSL and GoPro to do just this, to kind of leverage this technology, but have surfers do photogrammetry in reefs and kind of do like a rapid fire reef survey that's just accessible to everyone. And there's a lot of good tools for citizen science for terrestrial environments, but it's kind of lacking for marine environments. And I think that this would be a really powerful way to kind of implement this. Again, a lot of people have GoPros or action cameras, and so that's a lot of potential for people to survey their reef. So in conclusion, in the first chapter of my thesis defense, I did the first comprehensive analysis of underwater photogrammetry performance between DSLR and action cameras across a distant gradient. And my findings will inform potential surveyors and facilitate methods optimization. In chapter 2, I developed methods to integrate photogrammetry assets into a mobile augmented reality application. And with this, hopefully I've proved that technological progress is poised to promote science equity by allowing unfettered access to information that is out of reach for most. And with that, I'd like to say thank you to everyone that showed up on Zoom, in person, my committee, John Burns, Brady Weinberg, Drew Gray, my TCBES faculty, mega mentors, interns, dive buddies, and app testers. And with that, I'll take any questions. All right.
So if we look through testing cameras, that were from maybe like the, early 2010s era, and moving forward through time, like, obviously, camera with a bigger sensor is always going to outperform, sound cameras. But the current level of action cameras and moving forward as they continue to improve, do you think that that quality gap is going to be narrowing, like through time? Like, will the accessibility of these cameras outshine the level of performance to do, spending 10 times more?
So what John Graves asked was, as action cameras get better and better, will they eventually catch up or meet the performance of high-end DSLRs? You say that?
Yeah, we're like close enough.
Or narrow the gap. Yeah, I definitely think that gap is going to narrow for sure. Back to that WSL GoPro kind of project that I'm working on with the Mega Lab and Crispin here. We're using a GoPro Hero 11, and the results with that are really impressive compared to the GoPro Hero 4. So that's a lot of changes, a lot of sequential models there between the 4 and the 11, but the results from that 11 were and are pretty promising, and it would be really interesting to do this again or add that into the fold, because again, the DSLR I used here was also kind of like a mid-level DSLR. So you could do a whole spectrum of here, but I do suspect that gap is narrowing, especially if you tie a dollar value to that. I think that's you get a lot of resolution for your dollar, especially with like the Hero 11, for example. All right, Danny Paolo.
When you say about traveling in time, just that's just such a beautiful and powerful. And I also like the idea of using the community to collect data. I think that's really, really cool. And I was just imagining, it looks like the methodology to collect this data is quite specific, right? So you should do the transact, you have a window, so you imagine like surfers making like rashers on how to do this pictures and everything?
Yeah, so Danny asked if there's the methodology here seems in building these models, collecting this information can seem tedious or complicated. How would you theoretically communicate that to someone that's never done that before, like maybe a surfer? And it's not easy, but the methodology is really resistant to user error, especially as cameras get more powerful or generating higher quality imagery or suffering less from things like motion blur. And GoPros have those wide angle lens, which allows you to catch a bigger area of the environment. And that kind of prevents holes in the 3D model and kind of opens up access to more people. So it's definitely not easy, and it hasn't happened yet, but there's a lot of opportunities to kind of trial this with maybe kids that come into the Mokupapapa Discovery Center downtown and test it out on them in the same way we would surfers theoretically down the road and see if they can do it or yeah. So it's not easy, but it's not overly complicated. And another thing is there's just more tools than ever before. And not only has sensor density increased, but processing power has increased. So in the past, you need basically a server rack to generate some of these 3D models, or at least a computer with a big GPU or something like that. And nowadays there's cloud processing where you can you can send your photos to a processing center that's offsite and have them, you know, churn out the 3D model and then download it to your phone. So you're kind of detached from that process. And phones themselves can even generate pretty high quality 3D models. So thank you. Yeah. Yeah. So GoPro does publish the lens characteristics. So photogrammetry software like Agisoft Metashape and Pix4D can use that to kind of correct the imagery as it comes in. And on the other end, there's GoPro also has like an their app. They have like a prototype open source version of their app where potentially if you have programming chops, you could maybe have an app that's is connected to the GoPro and kind of builds the models on your phone, or at least does some of that like leveraging for you. But thank you, Dan.